and then we can build that. Right now, what I have done is taken this geometry coordinates and I have built that geometry. Okay,
Okay.
like you will be doing parametric study, right?
Yeah, yeah,
You will be optimizing things, band gap and that, right?
yeah.
So there it will be better that if you like this is 50, right? So
Hmm.
you write this in terms of a by something, a by something, some ratio. It will come all in some ratio, right?
Okay.
That design part. Okay.
Okay.
So after doing this geometry, should I move ahead or you need more little bit?
Uh,
Geometry we can do.
this is the 2D part or 3D part?
This is 2D part. First I will show you 2D part.
Okay, okay. You can
Then I
move.
will show you 3D.
Okay, okay, okay.
Okay.
Yeah.
Okay. So after the geometry, since we are using two types of material, one is acoustic and there is one solid material, the previous solid material. Okay.
Okay.
So this is the property that has been given in the your paper,
Yeah. Okay.
testing paper. So I use that same properties, and for air, I have used the inbuilt property. Okay.
Okay.
Okay. Now I can move ahead,
Yes, yes.
or if you need anything.
For the material,
Hmm.
if we want to input viscoelastic property, how we do that?
Okay, I will come to that later.
Okay.
Okay. This till this okay, right?
Yes, yes. Okay.
These are only material properties. Okay.
Yeah.
How do
Okay.
they define it separately? Those two we had problem, right? Defining air and the
Uh,
No,
material.
he built the model.
what you do, you can come here, right click, you will get a blank material. Okay.
Hmm.
So here you can add different materials, what property you need. Okay.
Okay.
Based on your physics, some property will automatically come up here, like here. Okay. And you
Okay.
can see here, these are tick properties, right? These are tick. It means these properties are being used by your physics.
Okay.
Okay.
So
Similarly for air.
for solid mechanics, these are the properties.
Yeah, right. These are property that are being used.
Okay.
Similarly for air, only density and speed of sound are being used.
Okay.
Now, this is your solid domain, solid mechanics domain, right?
Okay.
This is your pressure acoustic domain. Okay.
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 How we define it? Will it be
I will show you. So this is your geometry. Just select the domain. There
okay?
is domain selection. What you can do is you can select manually. Just
Okay.
click it here. You can select anything. Okay.
Okay. Okay.
So for our case, this is the solid mechanics domain, right?
Yeah.
Okay. There are all domains. You can select it here. Okay. Then you
Okay.
can delete from here. Okay. So better just do it manually. It
Like
will be
this
better.
Okay.
because he built it there, right?
Mm.
And we cannot select it like this.
Hmm.
So if we are doing this 2D approximation, okay, right?
Hmm.
So this is must. Typically, wave speed for perfectly matched layer. Okay, you must check that this value is solid dot cp. Okay,
Okay. Typical wave speed for
wave
perfect.
speed for the solid that you are using, na.
Okay.
So there will be the wave speed, right? So that
Oh,
is
okay. So it will be automatically shown, or we need to type something here.
this will be automatically shown because you
Okay.
have selected this physics. This will be automatically shown.
Oh, okay.
If you are making it from by default, okay. But if you are using some, you have made something else, then you are improving that, and then there will be some other values also. Okay.
Okay.
So
And
then you have to see this.
uh, thickness is defined 1 meter or what?
This is
Hello.
Yes.
meter it has been defined, but 2D case they take it as a by default as a 1 meter. Okay.
Oh, okay.
This is by default. Even for if you have validated this one, here also you will get this
Uh,
thickness as a 1 meter. Okay.
okay.
One thing that you notice is discretization should be done quadratic serendipity. Okay, for this band gap analysis.
What is meant by it? quadratic serendipity.
This is you, you know how we discretize these things.
Is it related to mesh or?
One minute. Now consider you have a beam, okay?
Uh,
So how you discretize this? You take 2 points, right?
yes.
You can take 3 points, right? And you
Yeah.
can
Yeah.
either discretize it as a linear,
Uh,
like something like this, or you can discretize it as a cubic, right?
uh-huh.
This is the order you are trying to discretize
Okay,
the.
okay, understood.
Uh, this is a FEA part.
Yeah, 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 understood.
Okay. Mm. So after this, this is the part where which you were asking how you will put the viscoelastic material.
Uh-huh.
Right now, this is a linear elastic material. Okay.
Yeah.
So here you can see these are what are type of isotropic material. You can even choose anisotropic, orthotropic, and other materials also.
Mm.
Here these are your property that is being fed by your material property section, right? We have seen here, right?
Okay.
Okay. So you wanted to add a viscoelastic material, right? So you can add it here from viscoelasticity. Okay.
By right clicking, then material
There is a
model.
material model, right? So linear
Okay.
material, non-linear, elastoplastic, hyperelastic. These are different materials. Okay.
Okay.
Using this, you can change the different types of material also.
There is no viscoelastic. Just now you showed
Uh,
this.
Come here and
Uh,
then.
okay.
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 Even
Okay.
you can induce some stress also. You can pre-stress this material
Okay.
and use this. Okay.
Okay.
Okay. So after this, we have initially the displacements are zero as we are doing eigenvalue analysis. Now come to this periodic condition. Okay.
Mm.
So for the unit cell, if you see,
Free. What is free one?
even is the it's a boundary condition,
Mm.
like such as free fixed boundary condition, like that.
Okay. Or
Robin
all
boundary
are free.
condition, right? So we don't have any
Okay.
now. If you see here, we have free boundary condition.
Uh,
Okay, why we have not here? Why we have not here? Sorry, free boundary condition here. Here we have na. You can see all this, right?
yeah. Yeah.
Why we have not here? Because uh, in the case of coupled acoustic, all these are the solids are interacting with the acoustics. Okay,
Okay.
these are acoustic structure boundary conditions.
Okay.
That's why these are not free conditions. These are interacting with the acoustics. Okay,
Okay.
so we have defined it as uh, free boundary condition, but it all has been overridden by acoustic structure boundary. You can see it here, right?
Okay.
Similarly, you can see the periodic condition and second periodic condition. Okay.
Okay.
Now for the solid case, you can see it here. This is your solid, right?
Mm.
This part will be periodic with this. So one you will turn this as SRC, then this will be your destination.
Okay.
Similarly, this part will be SRC, then this part will be destination. So that is what we have done for the Floquet boundary condition. Okay.
What is SRC?
SRC is the source.
Okay. So we should define this SRC.
You can select it here. One will be SRC and one will be DST. Okay.
By default.
By default.
For the first one we select will be SRC. The
Right.
second one we select will be
This.
destination.
So here there will be different type of periodicity, continuity, anti-periodic, flow plate.
We
For
use
you,
flow.
it will be flow plate. Okay.
Okay.
Now this is kx and ky. I will
Mhm.
discuss this later. Okay, kx and
Okay.
ky. Okay.
Okay.
So we are doing this 2D. So there will be kx and ky. Okay.
Okay.
Similarly, for this periodic condition, we have selected one is source and one is destination. Okay.
Okay.
Solid part is over. Okay. Now comes to the pressure acoustic part.
Mhm.
So this is your pressure acoustic domain. This one, 3, 4. So you can even exclude this 4 part if you think that this is not necessary for me. Okay.
Okay.
But if you want, you can select this. Okay.
Okay.
Depending upon how you are validating this part with the experiment. Okay.
Okay.
Sometimes what happens that inner part is cavity or something like that. Okay.
Okay.
So people remove that part based on their experiment. Okay. Now, this is your this eigenfrequency equation. Now I will come to this. So this is the property that has been taken from the material properties. Okay, the speed of
Okay.
sound and the density. Now this is sound hard bar. Since our geometry has all the part as a, like, see if you see it here. This is the unit cell, right?
Mhm.
So this part till here, from here to here. Okay, this
Okay.
is your boundary, right? And this
Yeah.
is free. Why this is free? Because this part is repeating, right?
Okay. Okay.
So uh, COMSOL will take this as a all the boundaries. This will take as a sound hard boundary, but
Okay.
as you put other boundary condition, this will be overridden, like acoustic structure boundary. Okay,
Okay.
periodic condition two. Okay,
Oh, we need to define periodic condition to the fluid as well.
right. You are repeating, na unit cell.
Ah, okay.
So like here, if you see it here, the way unit cell is repeating itself here and here, the pressure acoustics is also repeating here and here. Okay.
Okay.
Similarly for all the in x and y direction.
Okay. So we should maintain the consistency of
Right,
source direction.
right.
Okay.
Now, since we have done the solid, defined our physics, solid physics and pressure acoustics physics, right
Mhm.
now we will come to the where we are trying to couple the interface. Okay. So
Ah,
here, this is my solid domain and this is my acoustics domain, right? So this
okay.
is the interface we are trying to couple. Okay.
Okay.
So we have selected all these boundaries where we want to couple. Okay. Now,
Uh,
after
just
doing
just
this,
just a second.
uh,
This multiphysics we need to input in the beginning or
No, it will come. If we go select solid mechanics and pressure acoustic, multiphysics will come.
okay. Okay, okay, okay,
you
continue.
can, even if there is no physics initially you have selected,
Yes,
what
we
you
can
can
write
do
it.
is go to
Multiphysics.
physics, add physics here from here. Okay,
Multiphysics.
Okay,
We can.
no issues. Huh? You can
okay,
add multi-physics also. So
okay,
even if you can start from scratch and you can add everything.
okay,
Okay, now after that we will come to the meshing part. Okay,
okay,
so in the meshing part, come and select the size. Okay,
okay.
now once we will come to the size,
We didn't define the acoustic structure boundary interaction.
Can you go back to multiphysics again?
Acoustic
Acoustic structure.
structure boundary. And how did we define this individually? Where it interacts all these boundaries.
Oh, structure. Just select solid mechanics. Acoustic. Just select pressure acoustics.
Uh,
Nothing
there
much.
won't be other physics. Okay, so we have
Okay.
only from acoustics we have pressure acoustics. Like if
Uh,
you have taken the thermoviscous, okay, then you can select that acoustics as well.
okay. No need to touch anything else in this.
no,
No,
how
no.
the
Only you
attenuation.
need to select here boundaries.
I select
Ah,
boundaries.
Take care of boundaries. All your
Yeah,
boundaries are available or not here.
How how to select these boundaries?
Just click here. You will be like,
We need to select all the solid boundaries.
right, solid which is interacting with the
Fluid.
Uh,
acoustics or air,
okay.
because this is what multi-physics means, two
Okay.
physics are interacting. So
Okay.
acoustic
Understood.
is interacting with the structure. Okay,
Okay.
should I go ahead?
Yeah. 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 Sure.
Okay, then we will come to the meshing part. Okay, in the meshing part, just do the sizing, select the size, and comes to this, select all this. One more thing you need to you have mentioned that video lecture, right? That Chandra Prakash sir,
Mm-hmm.
right? What he says is that you need to take care of this message, right?
Hmm.
Mm-hmm.
That periodic boundary condition that you are selecting at the source and destination should be identical message, right?
Hmm.
Okay.
Right, that you need to take care of. So what you will do, you will just select it from, and you will, for him it was some other, but the meaning was same. Instead of identical mesh, they have something, some other term was there, but the meaning was same. Okay, because we have the updated COMSOL version.
Okay.
Okay, so meaning is same because the terminology they have changed. Okay, in the updated version. So what he has done was, he has done it this in the 5.2 or 5.3, I think. Right?
Okay.
Have you
Uh,
seen? No?
Yeah, yeah.
yeah. Can you clear this mesh and do it for now?
I
Do.
will tell you. I will tell you one magic trick also.
Okay.
Don't worry. Uh, what is the magic trick? I will tell you. What he explained was, he had explained with some old version. Okay.
Okay.
Okay. So when he had explained with the old version, at that time, with the structure and acoustic, it needed to be meshed properly.
Uh,
Means you have to properly, like he has used mapped mesh with the, from the identical he has used the mapped mesh, I think, right?
yes. Yes.
Yeah. So if you see this identical mesh one and you select this, whatever the mesh is here, it will
Mm-hmm.
be here. Okay.
Okay.
Similarly, uh, this side and this side, all the periodic boundary condition will be identical. Okay.
Okay.
So what is the trick? Even if you don't do this, user control mesh. Okay. What you do is you do the physics control mesh. Why we are choosing physics control mesh? Because in the old version, the meshing needs to be done
Manually.
manually. But with the newer version, it has already, it can do on its own.
Hmm.
If there is need, then you can do manipulate it. Okay, like this. I have selected mesh one, and what I have done is physics control mesh. I have done nothing. Okay. Now I
Okay.
will do is I will build this.
That's what we did. This,
I will
this
show
week.
you how you can check and manipulate that. Now, can you see any branch from mesh? No,
No.
right?
No.
This
Yeah.
is till now physics control mesh. Okay. What you do
Okay.
is you just go and select physics user control mesh. Okay. Now the physics control mesh has changed into user control mesh. Now you can do all those manipulations if you want, or if there is
Okay.
need. Since what I can see is I don't need, because all these the recommendations are already there, right?
Okay.
So we don't need to bother about this messing.
Hmm.
If
Okay.
there is need, what you can do, if they consider this has been given as your user control mesh, and there is this identical mesh is not there, what you can do is you can select all those boundaries needed for you. Okay. And one more thing, we have selected this discrete meshing. The elements are free triangular. Why? They have actually, the physics has automatically given, and your paper that you have shared me, that is also free triangular mesh. I think somewhere it is there.
Yep.
You can see it here, triangular mesh, right?
Yeah.
So right now meshing I have done is
This is control.
user
Physics
control
control.
mesh, right?
Okay. Yeah. Okay.
And I have used a normal. Okay,
Okay.
what you can do is, for the just this is just for the demo purpose, that was I have taken the normal because it takes time. Okay,
Okay.
what you can do when you are doing your part, you can choose the extremely fine. Okay,
Yeah.
and then you can do. So this is over. If you have any question, you can ask for here, miss, about miss.
Yeah. So far, okay.
Okay, now we have prepared our physics, we have prepared our maths. Okay,
Now
what we
start
are going to do is we are going to the
sweep parameter.
sweep parameter. This one. This you know, na? This
We
brilliant.
want a bit explanation on how we select the
Uh,
values of kx, ky, and how do we span the vector. Yeah, this.
so this is little bit different from CC sir, I think. Okay, so what he has what he had done, I will explain you how I do and a blog on the console do, that I will tell you. Okay, so okay, so this is your brilliant zone, right?
Mm-hmm.
This we term it as gamma, x, and m,
M.
right?
Yep.
Okay. Now, when we are going from gamma to, sorry, from gamma to x, what you can see, kx is increasing from 0 to
Two.
pi
Oh,
by lx, right?
yeah.
And ky is
Zero.
0, right?
Yep.
Okay. So, this is what we have done it here. Okay.
Mm.
For first part, we have, sorry,
No problem.
for first part, when we are moving from 0 to x, we have selected pi by a1 into k. Okay. And ky as 0.
Mm.
Okay.
Mm.
Now, when we are moving from x to m,
Mm.
kx value is constant, that is pi by lx.
Mm.
Okay. And ky value is increasing, right?
Yes.
And hello.
Yes. Yes. Yes.
Okay. Ky value is increasing, and it is increasing. So if you see it here, if this part, this value is constant, pi by a1.
Mm.
Okay. And this value is increasing.
Yeah. The k minus one times pi over a.
That
Where
I
do
will
we go?
tell you later.
Okay.
Just
Okay.
wait. Okay.
Okay. Thank you. Thank you.
Now, because it will complicate if I tell everything at same
Okay.
time.
Okay. Okay.
Now we have reached here. Okay. From here now, we are coming from M to gamma. Okay.
Mm.
Now if you see it here, what is happening right now is kx is decreasing, ky
Mm.
value is also decreasing.
Yes.
Right. Now see it here. This is 3 minus k and 3 minus k into pi by a1.
Mm.
Okay. So as we will feed k value, we will increase. Okay. What you can see is this is 3 minus k, right?
Mm.
So as k value will increase, this will decrease.
Yes.
So we have normalized it such like that this will from here to here, this will become 0
Mm.
when it will reach it here. Okay.
Mm.
Now I will explain what is k. Okay.
Mm.
So if you see it here, this is gamma, this is x, and this is m. These are
Mm.
three reasons from gamma to x.
Yep.
From gamma to x, one reason, x to m, second reason, and m to gamma is third reason.
Mm.
So I have divided this in a three regions. So I
Mm.
have 0 to 1, 1 to 2, and 2 to 3. Okay.
Mm.
K is a random value, that is, we are setting it some value. Consider it 0.05. Okay, something like that.
Just sorry to interrupt. The value from m to gamma, it should be from 2 to 0. Why 2 to 3? It is returning back to gamma, right? It should be 2 to 0, right? Not 2 to 3.
Tell me again.
The
The third M2 gamma, it should
Um,
be 2 to 0, or is it 2 to 3?
okay, I understood your problem. Okay, this is not an issue.
okay, okay.
Uh,
Just for representation.
Yeah, yeah,
if
okay, okay,
I will explain what is happening.
okay,
Okay.
okay. Thank you.
We have divided this section into three parts. One
Hmm.
is k is going from 0 to 1,
Hmm.
then k value is going from 1 to 2 and 2 to 3. Because when we are feeding into console, okay, it needed to be fed with a condition like such as if.
Hmm.
Okay, so what we are defining is k to 0 to 1 means k is moving in the x direction.
Okay, okay.
Okay, k is moving into 1 to 2 means it is moving in the y direction.
Vertical direction.
Okay, when k is 2 to 3, it means it is moving in the this direction. So that is
Hmm.
what we have done it here. Okay,
Hmm. Okay.
okay. Now one more thing. Okay, here you are seeing this is as a A1 and A1, right?
Yeah.
So this is from your what is in your paper. This is LX and this is
Lattice constant.
LY. Yeah, lattice function. Okay. Since both are same, I have taken it as A1, but it will be proper that if you write it properly. Okay, LX and LY.
Hmm.
Okay. If you understood this, now.
I guess the part that we use k minus 1 times pi, how we get this 3 minus k times pi over a. This one is still not clear.
Uh, okay, okay. Should explain it little bit more. Okay, just take k some value. This is 0.
Sorry, actually, we are very new to this, so we don't understand quickly. Yeah?
Actually, he said that he had done this. So I thought you
Uh,
understood.
Yeah, we just followed YouTube video.
we want the concept behind how do we do this equations.
We just copy pasted whatever. Uh,
K values they use.
yeah.
Okay, take some value k equals to 0.05.
Hmm.
Okay, so k small k. Okay, so when we are parameterize this, we are parameterizing this. Okay, just when we are taking the parametric shift, we are taking the k values from 0 to 3. Okay,
Hmm. We don't. Let us see.
so initially we are taking k value 0.05.
Hmm.
Then we are adding some values and we are going till 3.
3.
Okay. Now consider you have the first value.
Mm-hmm.
This is less than 1. Okay.
Mm.
So this value is
Pi over a.
okay. Now maybe pi by a1 into some k. Okay.
Mm.
This will become 1. I mean, sorry, pi by a1 into k. So k value will become 1, right? At some point.
Yep.
So this will reach here.
Point 1.
There will be some coordinates here, like you are increasing k. At
Yes.
some point, you will reach here. When k value will be 1, you will
1.
reach here,
Yes.
right?
Yes.
Okay. So, and kx value is increasing and ky value is 0.
Constant. 0.
Now, from here to here, okay, you are still increasing the k value. Okay, now k value is has surpassed 1.
Mm.
Okay, now kx value is constant
Mm. Yep.
and ky value is increasing.
Increasing.
So, it's increasing. You reached here, right?
Mm.
When you will reach it here, the k value will be 2.
Mm. Oh, I understand. I understand why k minus 1 because it starts at 1. That's why k
Ah,
minus 1. Uh-huh.
And similarly, now you have reached here, okay, and now you want to go here, okay.
Hmm.
So we are
It's
taking
Hmm.
points,
Hmm.
and then you
Okay,
will.
we understand. We understand.
Mhm.
Can we use this kx and ky every time when whatever design we use for analyzing band gap? We can use the same kx and ky expressions.
It will depend upon this LBZ
Depend
and
upon
this.
the brilliance one, but we want
Right.
to keep it same, so we can use the same
Most of the
equation.
time, this will be same. Most of the
Yeah.
time.
Here the unit cell is 100 mm. We have 10 mm unit cell.
That will change the lattice constant, but that
Uh,
expression will remain the same. Kx and ky will be same.
Yeah, I'm going to ask.
if
Yeah.
you see it here, we have normalized this, right?
Yeah.
Uh,
Pi by Lx.
So it doesn't matter.
So this value and this. So since your unit cell is like this, right? So we are
okay.
moving like that. This is same as any other LVZ.
Mhm.
Okay, so we can use the same
Yep, we
expression.
can use the same expression.
Okay. So I should move ahead.
Yes,
Yes,
yes.
yes.
Thank you. Thank you.
Okay. Now I'll come back and I will show you that parameters that I have shown you here. This is the kx and ky that I am varying.
Mm.
This is the n value. Okay. So this is the number of eigenmodes
We
that
used
we
to.
are trying to find. Okay.
Mhm.
This is your lattice constant. I have
Sorry,
written
and how 36?
since your paper is saying 36, I have taken 36. If you want more, you can add more.
Okay. It doesn't matter to the band gaps,
No,
right?
no.
Ah,
Actually he wanted till 12,000 hertz.
the resolution.
12,000 hertz frequency bandwidth. So he has taken 36. Okay.
Okay.
Now this A1 is your LX and
Mm.
A2 is LY. And this small k is your this random initial values. Okay, that we will be parametric sweeping from 0 to 3 with
Mm.
a increase of 0.15.
Mm.
Okay. Till here it's okay, right?
Yes, yes.
Yeah, yeah.
Okay. Now,
Can you show how you select the parametric sweep from different 0 to 3? Yeah, how do you add this?
okay, just here there will be this.
Yeah.
And since we have added all these variables in a parameter, okay,
Mm.
so this will come up automatically. So if we want, since our parameter is k, we can take this as the first one. If the parameter was n, you can select it here, and here you can add the range,
Mm.
start, step, and stop. There are different functions also that you can use. There are different entry methods, number of values, logarithmic that you
Mm.
can do. Okay,
Okay.
and you can if you don't need this, just delete this. Okay.
Mm.
So range is automatically selected when we select this 0 to 3 spans.
No, not automatic. You have to feed this here in three method.
Okay.
Start, step, and stop.
So
Okay.
what does it mean? Okay, can you?
Means start means from where you are starting. I am starting
Yes.
from 0 and I am going till 3. A
Okay.
step means that increment.
At every 0.15.
K is
Uh,
increasing.
it will increase.
Okay.
Okay.
So if we take what happens if we take 0.01, it will be much finer.
Yeah, right. It will be much finer. And the number of values of the parameter will increase, right?
Mm.
So
Okay.
less number of parameter means faster calculation. More number of parameter means it will take some time.
Okay. What will be the output if it is more number of parameters? Are we going to see?
No, no, no. Output will be same. I
Okay.
will explain this question in the result part. Okay. I will
Okay.
take the I will discuss this part. Okay.
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 Okay. Now we are doing a band gap analysis.
Yep.
So we are doing this eigen frequency analysis, right?
Mm.
Now, so this is your desired number of eigen frequencies. Right now I have written it directly 36. But if you recall here, we have
Hmm.
defined it in terms of
36 geometry
n
parameters.
equal to 36, right?
Yes.
Okay.
So you can directly put n here, uh, here 36, okay. And since your geometry is in mm, okay, so
Uh,
you will get around kilohertz, but you also want from 1 hertz to around 12,000 hertz, right?
Hmm.
yeah.
So search for eigen frequencies is 1 kilohertz. Now about this search method around this. So sometimes people take this larger real part, sometimes people take this closest absolute value. Okay.
Okay.
Application.
Which is the best one to choose here?
It will be better if you choose the larger real part or absolute value. Closest in absolute value, these two.
Okay.
Because imaginary part has no significance.
Okay.
Now, since we have coupled this, right? So we are taking this
Mhm.
solid mechanics and pressure acoustics solve for both, okay? And this is coupled. Okay, so this is important. This eigenfrequency is solving for this physics interface.
Okay.
Okay. Now this is your eigensolver. Okay. Now you want to solve for a relative tolerance of e to the power minus this. You can decrease this value as much accuracy you want. Okay.
So by default is 1
Here
e
you
power
have to,
minus.
this is the residual value. Okay.
Okay.
I mean, you understand what I am telling residual
Yeah,
value,
Yes,
yeah,
right?
yes,
yeah,
yes.
understood.
Mm. Now, if you have recalled with the that video lecture, he has what he has told is transform eigenvalue linearization point, right? So he had put some normalization factor. Venkat,
Yeah, yeah.
can you recall that part? You were telling now.
I don't remember this one.
Uh, so for his geometry was in micrometer, okay.
Okay.
So he needs that part, okay.
Okay.
For our case, then we will be doing since our geometry is 1 to 12,000 hertz, and his our in case is in mm, okay.
Okay.
So we need to tick this part. If it is necessary, the solver will automatically do this because this version is updated version. Okay.
Okay.
What this solver do is this automatically consider this your material and it takes the value. Okay.
Okay.
If you go to the older version, you need to put those things and you need to go through the document with the eigensolver document. What are the different steps? I think you have gone through that video. There will be he will be showing one slide also of the solver settings, right?
Yeah, yeah.
Closest real, closest to absolute value, and he will be
Okay.
showing this closest to absolute
Yeah,
value,
yeah,
number of frequencies, and what are the different this, and then there will be he will be showing to the eigenvalue solver for the transform, right?
Okay.
So this automatically it does. Okay, so now this is your solver. So this now since this is updated, you don't need to worry. Now you can see it here, your parametric values that it will be solving. K to 0, 0.153, and these are this will go to 3. Now after doing this, what you need to do, you go
solve.
to the study and just click compute. Okay.
Good. Okay.
Okay.
Once you will do this compute, you will get a you will come to result section. This is all of this is over. Now, after coming to result section, what you do is you just
One
select a
more.
1D plot group. Okay.
Hmm.
Okay.
In the 1D plot group, you select a global.
Hmm.
Okay. So you will come to here, this global. Now, you are trying to plot the band diagram, right?
Hmm.
To plot the band diagram, you need X and Y, right?
Hmm.
X data is your parametric variable that you have taken, that is a
Hmm.
small k.
Hmm.
Okay, and y data is frequency, right?
Right.
So I will just write this frequency. and in X data, I will be plotting is a small
Okay.
x. Okay. Now, this is important. Here you can see there are different values, okay, inner, outer, and all solutions, right?
Mm.
So here I have taken outer solution. So what happens is this stores in a matrix, okay, all these values for each case there will be frequencies, right?
Yep.
So if you take the outer solution and just plot this, you will get this diagram.
Mm.
Okay.
Now you can see the band gap. If you can see there is band gap from 1000 to around this is
Mm.
1100. From then it is 1205 to you can go 1977 around.
Mm.
Similarly for each. Now
Yep.
this is the coupled one, right? Now come to this uncoupled one. Now since you have validated this, right?
Mm.
Hmm.
You can see the band gap here is more, right?
Bigger.
Right. And this has gone till 12,000 hertz,
Mm.
the 36 mode, but this one has gone till
5,000.
5,000.
5,000 hertz,
We need to
right?
increase the number of modes.
Right. So this is that part, okay. If you have any question, you can ask.
The paper didn't use coupled, right?
No,
Hmm.
paper doesn't use couple.
But both will give the same results, right?
Hmm.
No, no, no.
No different. When
Little bit different, but if you compare this, na, uh, like if you see from here, you are getting from 1310 to 2529 hertz gap,
Mm.
right?
Mm.
Here you will see
around same.
this is 13, then this will be around 1000. So if you see it horizontally, more or less it will be same, but the
Mm.
gaps are now acoustic modes are also have come into this. Okay,
Mm.
understood this part?
Yep.
Yeah,
Yep.
yeah, understood.
So this frequency range means this is till 36 mode for the coupled one, and this was
Mm.
36 mode, and this has gone till 12,000 hertz because this is only considering the modes of the structure,
Mm.
and this is considering the both. Okay.
Okay.
Now after this 2D, now come to the 3D part. This is okay, na?
Yeah,
Yeah,
yeah, it's
yeah,
If
yeah.
you
okay.
have any
2D
question.
part is okay.
Okay.
Now come to this 3D. So for the 3D case, I did the same way. I did the geometry. Now if you see, take all those coordinates and drawn that. After then I have extruded this geometry, the drawn coordinates. Okay. And since I needed a unit cell, because if I am coupling the acoustics, so I need that domain. So I build a block also. Now my geometry is ready, right?
Come again. Can you repeat this again?
Okay, I
After
need
extrude?
this acoustic, okay, right?
Okay. Uh,
This acoustic domain, right? So what I did is I selected the block from here. There are different
okay.
geometry here.
Same like rectangle in 2D.
Right. Yeah, right. After the geometry, I hit the material, selected the material, air and this material. Okay, so this is I don't think I need to repeat this, right?
Yeah, yeah,
Yeah.
yeah.
Ones are being used. Similarly, this is your pressure acoustic domain. This is your solid acoustic domain.
Mhm.
This is your pressure acoustic domain. And what are the properties are being used? You can see it here. Then this is your sound art boundary wall. Then this is your initial values. Initially 0. Now this is your periodic condition. Now this is your, again periodic condition. Similarly, with the solid elastic, this is your linear elastic material. If you want to use viscoelastic, you have to just choose the viscoelastic. This is the initial values. Now this is your periodic condition. Okay. So flow periodicity, I have taken kx and ky. Okay. And kz For now, I have taken it as a 0. Okay. Now, based on your requirement, okay,
Hmm.
based on your requirement, now if you now based on your requirement, what you can do is you can select that LBZ region. Okay. Right now, what we have selected is KX and KY, right? If there is in 3D, this is it for the two dimension, right? For 3D case, you can select the KX, KY, and KZ. You can take that LVZ region based on your requirement, the way you think the wave is propagating for your problem. Okay. Right now, what I have taken is I have varying the KX and KY, K and KZ. I have kept it as a 0. Okay. Now, so this is your flocket boundary condition, Kx and Ky, and this is varying same as the 2D case. Okay.
Yeah. If you keep Z as 0, then there's no difference between 2D and 3D case, right? It will be the same, right?
There will be different because at in the previous 2D case, the Z part was not there. Okay. Here the geometry is there, but wave is propagating in only in X and Y direction. We are
Yeah.
trying to force.
Meaning we're
Okay.
propagating Z.
If you want KZ, we can put it here, but because
This way, this
we
direction.
don't have any reference to that, okay,
Equation. Hmm? Not equation.
we have only chosen KX and
But it
KY
was
here.
0, right? So there's no weightage to it. There's no wave propagation in Z direction.
If you want, you can choose that. And similarly, what you can do, the way we have taken for 2D case LBZ, right? What you
Yeah.
can do is you take a 3D, make a 3D unit cell, okay,
Hmm.
and choose your domain such that it make one unit cell, right?
Hmm.
This will go in one direction, then, and make this. So you need to take 1, 2, 3, 4 like that.
Okay.
Hmm.
Okay. But for now, what I have done is I have only taken in the Kx and Ky direction. And Z direction, I have kept it as a 0.
Normally for band gaps, I think KZ is 0, right? KZ they kept 0. They usually use KX and KY, right?
In most of the papers, what they do is they only do study in 2D. But
Hmm.
in seismic metamaterial cases,
This
okay,
matter.
if you have gone this ground vibration
Hmm.
metamaterial, uh, in that cases, they use this KZ also.
Hmm. Okay.
Now, this is okay, then I can move ahead, okay.
Yes.
Yeah.
Yes.
Now, this is the multi-physics and acoustic structure. Now, instead of edge, we have boundary here.
Hmm.
You can see it here. Right?
Hmm.
So this is that couple. Now coming to mesh. Now if you see it here, I have no branch of the mesh.
Hmm.
I have directly used physics controlled mesh.
Hmm.
I have used the element size normal,
Hmm.
and if you can see the frequency, I have chosen the maximum frequency that I need, and this will be dependent on the depending upon your need what you need.
Hmm.
Because the paper was that 12,000 hertz, so I put it 12,000 hertz.
Okay. So number of modes will be automatically defined. So we don't need to define the n value in
No, no,
parameter.
no, no, no. That you need. This is just for the meshing purpose. Okay.
Okay.
That lambda by 6
Yeah,
thing,
yeah. I know. One
for
sixth of
that.
the wavelength.
Uh,
Why do we have to hold that?
so if you want to check each part, what you can do is you can convert this physics control mesh to music control mesh. And you can check this identical mass mesh is there or not. Okay.
Okay.
Now meshing is done. Now come to this study part. Similar thing is there. We are moving to the K from 0 to 3.
Hmm.
And if you come to this study, properly see that you are using this mesh or not. You can even modify. By modifying, you can disable these all these. If you want to study individual, you can disable the other one. Okay.
Okay.
So now, now if you see that paper is only one, right? Solid.
Yeah, yeah, yeah.
So you can define different study here only, and what you will do is you will just define this study here. So this will solve for one physics.
Ah, okay.
Now I did this compute. After this, I got this. Now, if you see this one, because of there is three dimension, right?
Direction band gaps.
So there is some variation in the initial phases.
Okay.
Okay.
What do this directional band gap show? I mean, the one you see now is a bit. There's no full band gap right now.
Ah, right. This has come because we have considered our geometry to be in 3D. So
Mm.
the third dimension will also come as a factor.
Okay. We are asking what
So
is the significance of this?
Yeah,
How we interpret this?
for this, you need to read the some of the papers, okay, which they have done in 3D. Okay, so there they will be explaining all of these things. Why? What is the some of the papers? If you see, even if there is this line, they take it as a band gap in the
as a
3D,
band gap.
in the three
Ah,
dimension. Like if you go through the seismic metamaterial part, they have done this study in three dimensions. Okay, and even if this is there, they consider this as a band gap.
Mm.
So I, you have to go through some literature for this part, for
okay.
the three-dimensional part, how they take this as a band gap.
What about the directional band gap? Do you have idea about this? How it is different to a full band gap, and what does that reflect?
Uh, I don't have any idea.
Ah,
I
okay,
don't.
okay, okay. Thank you, thank you.
So this is from my part. If you have any question, you can ask.
Yeah, actually, the unit cell which we are using
Importing
is importing is complex, and it will be hard for us to
designing COMSOL.
yeah, make that in COMSOL.
I think
Can you?
since you are not aware of COMSOL, you are thinking it as a hard and tough.
Yeah,
If you work 2 3 days, you will be able to draw this in COMSOL. Since when I first saw, I think how they had done this, but uh, now if you see it here,
Mhm.
now this is your center, right?
Yeah, yeah.
So this will be having some length. I don't know how you have defined this geometry, but this
Uh-huh.
will be given, right?
Yep, yep.
Yeah, yeah,
A or something.
Mm,
This will be some angle theta,
mm,
right?
yeah, yeah.
What you can do is you can find all these coordinates using like it will come as a cos theta plus b for
Okay,
x1. Okay, for x2 you all do thing in a and b and theta.
okay.
Okay, after this what you do is one more thing also you can do is you take a excel sheet. Okay,
Mm-hmm.
and like these corners are fixed.
Okay,
Size may vary, like this will be sometimes bigger or this thickness may be bigger. Okay, but these coordinates will be number of corner points with number of corner points will be fixed, right?
mm,
Only the unit cell is size will only increase, but the number of corner points will be fixed.
okay,
So you write all those coordinates in this and then import all these coordinates there in the console and make this diagram, draw this, so that when you are doing the parametric study, you can vary these parameters also and see those band gaps also.
okay.
Do some geometry exercise. Once you will do, then you will be able to do only.
Uh,
Okay.
so the other way, it will be hard to import or
No, not hard to import. Problem is Then you need to do lot of geometric operations,
Oh.
because when I had first file that he had sent me, what
Mhm.
happened when I imported this into my, since it was in console, there was a file which was imported, right?
Mhm.
And I was selecting the boundaries,
Okay.
periodic boundaries or the interfacing boundaries. I was not able
VPS
to select those file
You can
boundaries.
select.
So it is difficult for, so you need to do these geometric operations, rigorous geometric operations.
Okay.
It will be better if you draw all these diagrams there only.
What happen if we import the unit cell only and draw the block?
Same thing will happen. This is
Okay.
important. Now, block is not much simple. Block geometry is simple.
Mhm.
For this, you will need rigorous then thing if you import that. What
Okay.
I will say is any unit cell is fixed with some parameter A, B, theta, C, right?
Okay.
Find all those corner points. What is the corner points coordinates? X, Y, and Z.
Okay.
Then draw.
Okay.
Or if it is a parametric, something like this, right?
Mhm.
So you need to draw this. You need some expertise on this.
Okay.
If we don't do acoustic structure interaction, we just do the eigenfrequency solid mechanics structure, then we don't need to draw it there on the console, right? Then we can import like we did previously,
Mhm.
just apply the periodic boundary condition. We don't need the interaction, then we don't need to draw it in the console, right?
Sir, actually, you don't need to make in the console. But the fact is, sometimes you will be having some issues with selecting the boundaries. Okay.
Hmm.
For that purpose only, I have told that it will be better that you make those geometry in the console.
Okay.
Then it will be easier for you. Initially, it will may seem that it is tough, but slowly it will be easy.
Okay. Mhm. How we will do now? Calculate the coordinates. I know another method.
Okay, should we bind up or we
So,
have?
so we select the polygon and then select table, and if we give coordinates, it will
Huh,
draw the lines.
right,
I mean the 2D sketch.
right. So like here,
Okay.
if you see, this is starting
So,
from this point.
after
And
drawing
then,
2D sketch, how to extrude it?
oh, so this is 2D diagram. We'll see in 3D. So in the geometry, you take a work plane. Okay.
Uh-huh.
So this is your work plane. In the work plane, first you go to this polygon. So first I make this
Okay.
individual coordinates. Okay.
Okay.
Then I made the outer cover of inner cover of this. Okay.
Okay.
After making this, what I did is I extruded this. So what it you just come here in the work plane, and here there is a extrude setting in the work
Okay.
plane. Extrude this, you will get this extrude. So just select this, and you can extrude this with a of distance, whatever the distance you need. Okay.
Mhm.
So after then you need acoustic medium. Then I made this block. And
Okay.
that's it.
Block will be, yeah, we don't need to give any dimensions.
No, no, you need to give dimension, na?
Okay.
100, and what is its
And
position.
how we know? Okay, corner.
You know
Understood.
na unit cell. You know your unit
Yeah,
cell. So from that you just put all these values.
yeah. Okay.
So you know how to draw the geometry using coordinates,
Hmm.
polygons.
Yes.
It said if we draw, then it's very straightforward. It's not really.
Okay.
If we draw complicated designs, though, then how will we define the coordinates? Still
No, no,
straightforward?
no, not only coordinate. This is a straight line. That's why I have taken coordinates. Okay.
Yeah.
Like if we see it here, this is the first point. Second point is a straight line. From first point to second point is a straight line.
Mm-hmm.
Then again a straight line. Straight line, a straight line. If you have other, then you need to use different. You
Geometrical
can use
figure.
the geometry. There is a.
Then why don't we turn
So
on
we
the?
can use a parametric also. Okay.
Mm.
You see here, there is a circular cubic interpolation curve. Okay. Parametric. You can select a parametric curve. Okay. And if you know that, like from here to here, there is some parametric. Okay. So you can put some values here. How it is valuing some parameter. Consider t is the parameter. Okay. X coordinate is varying as t, and y coordinate is varying as t square. So you can all do that in this parametric curve. There are a lot of things here. You can just need to explore this.
Mm, okay.
There are tutorials for this one.
Mm.
COMSOL geometry. Asking there are tutorials available for this one.
Yeah, if possible, can you send some links of tutorials for geometry?
Easy to follow for beginners.
Okay, I will share you with Venkat.
Okay.
Okay.
Okay. Seems okay.
Okay, then I close this session or
Yeah, we can.
Yeah, when we try to build a geometry first, because otherwise
um,
we wanted to do in front of you,
mm,
but now we cannot do because we don't have a geometry in COMSOL. We only import it from other software.
okay,
So first we would try to build a geometry by using the coordinates or by using the geometrical features, and then we will try to follow other steps that you have there.
yeah,
If we have problem later, then we will discuss with you.
okay. So, what is that next? I think Venkat is there or
Yeah, yeah, yeah,
yeah, Venkat. I think this part is over, right?
yeah, yeah.
So, the second
The
part
next
we will
one
move in,
also,
right?
I will share the paper. Maybe it is easy to understand, but we cannot understand from the paper itself.
Okay,
We are trying. We have a sample that 30 diameter with some
mm,
uh, yeah, rectangular pattern unit cells
okay.
similar to this.
Mm.
Uh,
So,
and
in that part, you need to measure this alpha, sorry,
Yeah,
yes,
absorption,
yeah, yeah,
yes.
yes,
Yeah,
yes, yes.
we want
reflection,
to
and
measure
transmission,
absorption.
right?
Yeah,
Yeah, yeah.
Only these three,
absorption
right? That
and
I will explain it.
how much sound it is blocking.
Reducing noise reduction.
Okay. And what type of material you are using there?
Polymer,
Polymer,
viscoelastic.
viscoelastic you are using it, right?
Yeah,
Okay.
yeah.
And what is the third part is there? There is
Third part is similar. It is of earmuff,
okay,
and we have this same unit cell designs as inserts
okay.
inside, and we want to see how
When
much
you are saying,
noise reduction when the
okay,
sound is from outside, and how it is reducing the noise
okay.
when the sound pass this.
You are saying polymer as this rubber only, right?
Not rubber. Actually, we are using shape memory polymer.
Safe memory polymer. Okay.
Yeah, but it doesn't. Yeah, we don't use the shape memory effect of it. So we can just consider it as polymer.
Okay.
And yeah, which material model is ideal for it?
Actually, most of the time they use this as a linear elastic material only.
Okay.
And like even for this, if you have done underwater acoustic, this
Mm-hmm.
pulverized coating or something, if you have heard it, mostly that is a rubber is a viscoelastic material, right?
Okay.
but they model it as a linear elastic material because the analytical part doing the viscoelastic takes lot of effort.
Yeah, yeah. I did these models in Altair.
Yeah.
In Altair, we yeah, obviously we cannot get these band gaps, and also we want to do this in COMSOL.
Okay.
So we are looking for, we are, as a beginner we try to copy the tutorials. We did something. Yeah, if there are errors, we don't know how to solve what we are missing, and all. Yeah, and we have less time to do this, so we
Okay.
approach you.
Yeah.
But you tell the geometry when we import, we have to do a lot of geometrical things to make them separate with the acoustic structural boundary. Is
Yeah.
it is difficult to do, or we can, because now we it will take more time to get familiar with the COMSOL geometrical features. Importing is straightforward for us. Can we do that particular thing?
Actually,
Or yeah.
it will take lot of detailed knowledge about that geometric operations.
Hmm.
Like you need to go in more detailed. Okay, like uh, always there will be always uncertainty that that boundary is present or not. If that is not present, then you have to do that partition. Different there are operations that you need to do.
So it is more difficult, easier
Yeah,
to draw it in COMSOL. Huh?
it will be difficult for you because you will be always, even if you import that and it is working. Okay, it is not that if you import that this will not work. You will get a domain, you will get a volume, different boundaries. It will work because this is a numerical simulation. Something will work, but how much accurate it, that will be a thing.
Hmm.
Like if you have here, when I am selecting this multi-physics, okay, some boundary may miss and you want it is complicated and you won't be able to see it. If I do this, you won't be able to see it if you are not seeing it. Okay, so that's why I am suggesting that even if you see different videos also, they are making this geometry in console.
Hmm.
It will take some time, but you can do that. I will share you some links within for the geometry part.
Okay. Okay.
Okay, then I will close this session, right?
Oh, yeah, yeah. For the second part, if you have the PPT which I sent you, can you open?
Okay. You can see this, right?
Yeah, if you see the sample here,
Okay.
uh, it is similar to what we are doing.
Okay.
So we have a sample at the end of tube, and
Okay.
this is a impedance tube.
Mhm.
Then there is a sound of 94 dB pink noise. Is it?
Yeah.
94 dB pink noise. What we are trying to do is measure the absorption coefficient of this sample.
Okay, that we can do.
So this we can import, right?
Right. We will see this part if we can import or not.
Okay. If you want me to send the sample, I think the air and tube you can manage. If you want the sample, I can send it for you.
You send me.
Okay.
One more thing is there.
And the
This
paper also, which we are
you are
trying to.
doing this in an impedance tube, right?
Yeah. Yeah.
Yeah, yeah.
Okay, so you are using BNK, right? This one
Yeah.
is big
BNK.
and this one is
BNK.
small, 29 mm.
Yeah, yeah, correct. We did
Okay, we
this
can
in
do this.
Altair, but yeah, Altair doesn't give
So
doesn't
you
have the.
want your impedance, sorry, in the see in the experiment part they do like this. Okay,
Mhm.
there will be a bigger and then there will be a smaller part because
Yeah,
you are
yeah.
measuring 29 mm.
Mhm.
On the but in the FEM What the
Mm.
people do is they do not consider this part. They
Yeah, yeah,
consider
yeah.
only this part only. Okay, and you can do this analysis. You will get
Yeah.
the same result.
Yep.
Okay. This one I did in Altair OptiStruct.
Mhm.
We can get the sound pressure at mic positions, but yeah, it is not directly giving any
Yep.
absorption
Yeah,
coefficient.
you need
So
some
yeah,
codes
it's
for
hard
that,
to correlate.
right? You
Uh,
need some codes and this IOSA standard also. That
Yeah.
uh,
formula is there, na? That
Yeah. From let's say.
in the
yeah, yeah.
experiment you have used it.
So this option is directly available in COMSOL, right?
Actually, I can even tell you some different method also. Okay, there are two, three methods we can do this. Okay, then this will we will see then. Okay,
Okay.
so I will prepare for this. You will share me this sample. Okay,
Okay.
this is 29 mm and share me these details also. This mic to mic difference and
Okay.
length of this tube also and dia.
Sure.
Okay, okay,
Okay.
Venkat. So I will
Okay.
just close this session. Thank you all.
Yeah.
Thank you. Thank you. Thank you
Thank
so much.
you.